Welcome to another podcast. In this episode, we're going to be taking a look at how to find tangent lines of functions which are defined implicitly. So I have an example for us to look at, and that is to find the equation line of the tangent to the curve. And I have an implicitly defined function here. And one of the things I want you to note about this function is we cannot solve for y explicitly. So this is not going to be the kind of function where you want to try to solve for y in terms of x. It's just not going to be a good idea. We could do it, but it would be very, very complicated and just not worth our time. So instead, we're going to use implicit differentiation to find the tangent line to this curve at the point -4, -1. And you could see that this is in fact a point on the curve, because if I let x be -4 and I let y be -1 and I plug it back into this, you should check this for yourself, but if you plug in those values you will get 22. So once again, this is implicitly defined because it's of the form f of x y equals c for a constant. So you have functions of x and y on the left, and you have a constant on the right. So it's implicitly defined. Now, I'm just going to kind of walk through the steps, and these are very similar to the steps we did in the previous video about implicit differentiation. So if you get a chance to watch that one, you should probably watch it first. So remember, the first step here, or step 1, is to take the derivative of both sides. And when I say both sides, because this is an implicitly defined curve, there's an equation here. So both sides of the equation. Okay, so I'm going to take the derivative of the left-hand side and the derivative of the right-hand side. And I should probably add that when I say take the derivative of both sides, I'm regarding y as a function of x. So if I take the derivative of y, I have to include chain rule in that calculation. So the right-hand side here, we have the derivative with respect to x of 22. So looking at the derivative on the left, it distributes, so I have the derivative of x squared plus the derivative of x times y minus the derivative, well, minus 2 times the derivative of y cubed. I'm using the linearity there. And the derivative of 22 is 0. So power rule says this is 2x, and let's talk about x times y. That's product rule because y is a function of x. So this should be plus derivative of x is 1 times y plus x times the derivative of 1. Or excuse me, times the derivative of y. So the derivative of y is 1 times dy dx. That basically just says the derivative of y is y prime, which it is. And then over here we have minus 2 times the derivative of y cubed is 3y squared times, because of chain rule, dy dx. So let me simplify things a little bit here. Alright, we've got it in a decent form, so that's pretty much the end of step 1. We have implicitly differentiated both sides. Step 2 in this process is that you're going to solve for dy dx. So you regard dy dx as a variable, which it is. It's the derivative variable. So we solve for dy dx. Because dy dx is included in both these terms, I'm going to factor it out, which means I'm going to have to subtract this over. So we have x minus 6y squared times dy dx, so pulling it out of both these terms, equals, and then if I subtract these over, then I get a minus 2x minus y on the right-hand side. Finally, solving for dy dx, because I factored it out, this factor is multiplied, which means I can divide it over. I don't subtract it over, I divide it over. And so we have this form. So in this form, I can find you the derivative at any point. Notice it's not advisable here to try to plug back in for y like I did in the previous problem, because all I really care is what's going on at one point. So that's what the third step's about. The third step is to evaluate dy dx at the point xy, which in this case is -4, -1. So our notation for that is we think of dy dx as an operator, and we're evaluating the operator at the point -4, -1. So that is equal to, I'm just going to plug in these values. And if everything comes out okay, this looks like you get 8 plus 1 on the top, so it's 9. And then it looks like you get -4 minus 6, so -10 out of the bottom. So this is our slope. This is the slope of the tangent to the curve. This curve here, x squared plus xy minus 2y cubed equal 22. That curve, that's the slope of the tangent line to that curve at the point -4, -1. Now, finally, since I'm trying to find a tangent line, the fourth step is to actually form the line. And we do that by using point slope form. So I'm going to use point slope form to find the tangent line. So recall that point slope form is y minus y naught equals mx minus x naught. And the values we have here is the y value that we know is -1. And the slope that we know is -9/10. And the x value that we know is -4. Now there's a lot of negatives running around here, so kind of make sure you keep everything straight. This gives y plus 1 equals -9/10 x plus 4. We got a negative here. And solving for it explicitly, we get -9/10 x, let's see, minus 36/10 minus 1, but I want to think of 1 here as being 10/10, just so I can get a common denominator and subtract. And so written explicitly in slope-intercept form, this is the equation of our tangent line. So there's two major products here. We've got the implicitly defined derivative, which basically is a clever way of saying we've got a formula for the derivative at any point. And we also have the actual tangent line at every point x as a function of y. So I took the liberty to graph this. And so if you look at the graph of this curve, what you'll see here is the red curve is the implicitly defined function. I had to use something called the implicit plot command in Maple to do it. And so I just plotted this curve. And then I also plotted our tangent line. You can see the tangent line being plotted here, and that's the blue dashed line. And so you can see the tangent line here touches this curve exactly at the point -4, -1. It's tangent to the curve at that point. I do want to remark on one thing here, and that is if you look over to the right, this is clearly not a function. This does not pass the vertical line test over here between 4 and 5. There are multiple points along that interval from 4 to 5 where we would fail the vertical line test because it would pass through at least 2 points of that curve. And so you notice that we're finding the tangent line to a curve and not a function. That's sort of a new thing for us. We have that ability now. We've done that before with parametric equations, but now we can do it with any implicitly defined function, or any implicitly defined curve for that matter. It doesn't have to be a function. But this is the benefit of being able to take a derivative implicitly. All right, thank you for watching.